Here actually what you have is you have different electric field, okay, 5, and here you have 4 thicknesses multiplied by 4. So it's actually 4, 5, which is 20 by 5, which is 100, multiplied by 3.5 hours each. So I really was spending a lot of time and consuming a lot of resources at LLB, and I actually was planning to say this at the end, but it's time now to say thank you very much for this, Professor Bouchard. I was even having many times the priority comparing to postdoc working in the lab, who has projects with NSF, with many organizations. So I really appreciate this, and I believe that this work cannot be done without having a dedicated instrument such I had in LLB. So thank you very much for this. Sorry for interrupting, Patrick, but I got the feeling I must say it now.
Just a few words also on the history of this work. In fact, we started this work, Osama said, 6 years ago, perhaps with another thesis, but with very bad tools in the lab. And thanks to the new tools, to the tools of Professor Bouchard, I think that Osama was able to do all this very nice work. And I'd like to thank also some people from Laplace laboratory. In fact, we started this study in 2005 with the collaboration of the CAN and the Well, some work on the work of Osama. In fact, in the presentation there is only a part of the work shown in the thesis, and in the thesis there is only a part of the work done by Osama. Because in fact, when Osama started the PhD, he was working on technology,
Packaging.
No, in the beginning, not
packaging. Technology, yeah.
Was in technology of main switch, and the objective was to improve the reliability of the main switch. Then he started to work on packaging, and then to work on AFM characterization, because he started to see his PhD and be working on this. And when he has seen that it was very interesting, he started after it was impossible to finish this thing. Then, in fact, all the work done has been done in 2 years and a half, almost.
Yeah.
Which is very, very impressive. And I want also to mention that this AFM characterization, Osama, for this characterization, Osama has developed all the procedure. I mean, I know because when I started this study with Mohamed Abdi, I have seen that it's very, very difficult. Because it's not, I think in the presentation it's not said, and in the thesis there is only few words. It's very difficult, it's very long to have a good understanding on how works the equipment and how to have a very good measurement. One question I have about this, perhaps, can you summarize what is the main difficulties for KPFM and FDC for this? What is the main problem we have to overcome? And what is the main advantage of FDC compared to KPFM?
Yes. So let's start first with Kelvin per force microscopy. If we want to optimize the parameters for the measurements, the interface of Kelvin force microscopy actually has like 75 parameters we have to optimize if you want to have really a reliable measurements. And similar to MEMS failure, these parameters also has multi-physics coupling. So if you change one, you have tens affected. So we spent almost 1 year and 3-4 months to understand these parameters and the effect of each one on the other. So if we are going to say what is the most critical parameters, I would say a parameter called lift scan height, which is controlling the separation between the tip and the surface. This controls the lateral resolution and avoiding the artifact of the surface. The second critical problem with these measurements actually with Kelvin force microscopy, which is not there in FDC, is the charge induced artifact in topography. What you do actually, as we mentioned, we inject the charge like this one here. When we inject the charge and then we measure the KPFM actually is based on measuring the topography first and then jump up and then follow the same to measure the surface potential. We measure topography in tapping mode. Unfortunately, this mode cannot differentiate between electrostatic force and the van der Waals forces. So if you have any charge on the surface, you measure wrong topography. Simply, the system will detect that if the charge is here, this is artifact of the surface, so it will go up far from the surface, giving wrong topography image. If it is wrong topography image, everything is wrong. We spend a lot of time trying to finding a solution to overcome this charge. We need the tip when it goes over the surface, and C charge is not to be affected during the topography, but affected only during the surface potential. There is many assertions this. One of these techniques is called feed-forward compensation, where what you do is during the topography measurements, you apply the same potential from Kelvin force microscope. So if you have any charge on the surface, you cancel this in topography, and then you remove this bias, and then you measure the potential. This has an effect on the charging. So we need to reduce this effect, and that's why the effect of the tip is important. So the critical issue is the lift scan height, the effect for charging in topography, and the other important parameter is the tip. If you change the tip you are using, you have completely different stuff. Because actually here, for example, actually this convolution of the capacitance variation in different areas are dependent on the tip shape. If you have lifting of the metal, you are done. You cannot spend any more time with these measurements. And it is impossible actually to do all of these measurements with a single tip, right? So what you need to do is to develop a calibration techniques for each tip you are using, and you use these techniques continuously during the measurements. This is not explained in the thesis. And I call this as really the secrets behind Kelvin per force microscope. It is not explained anywhere in the thesis. The other important parameter is a derived phase. The derived phase simply is the phase difference between the reference signal and the reflection of the AFM tip. If you do not understand what does it mean derived phase, it will lead to completely wrong surface potential measurements. And we have a lot of wrong results in the beginning because of this. So among the many parameters, this I believe is the most critical one. And the point is, if you solve one, this might affect the solution of the other. FDC, I like it so much because of these issues actually. It avoids many of these problems in Kelvin force microscopy. The calibration is easier than Kelvin force microscopy, so you don't need to be careful or caring about having this metal lift coating. So if you remove this, this is a very big issue. You can use any tip, but before you make a simple calibration, mainly based on the previous work of Professor Bouchan, it's also secret, it is not explained in the thesis, and then you can use any tip after that, then you make some sort of the convolution. The other important point is the tip apex itself. If it's changing in Kelvin force microscopy, it's a very big problem, while in FDC, it's not that serious. Finally, the surface potential amplitude you are measuring is really very immense because of the high electric field, which means when you measure the potential, be careful not to charge the surface. This is a very important message. People I have seen in some papers, what they do, they inject a charge, then they measure Kelvin force microscopy. But when you measure, actually, the potential of the tip is changing all the time until it equals to the surface potential, right? This makes a charging of the electric field. And what you need to do is to remove this. How to remove this? You have to understand many parameters in the measurements. Finally, how to inject a charge over the surface? This is a very big question. I have shown that the charge injection in Kelvin is in tapping mode. I did not explain why this happens. Why we need this. We need this because we spend like 7 months or 6 months injecting in contact mode, and at the end, everything was wrong. Simply because if you have a contact mode here, and it comes in contact with the tip, you have a metal coating. This metal coating will be